Okay, so this is your Timescale notes for students at Westside High School. So far we've been talking about all sorts of things in climate change. So we talked about causes, how their causes of climate change is usually more energy leaving the system or coming into the system of the atmosphere and surface of the earth. So right now what we know is we have more energy coming in than we have leaving, and that's largely due to greenhouse gases. We've also investigated how that carbon dioxide we can trace directly back to humans and fossil fuels. We've also started to think about solutions for climate change. Sustainability is the main focus, so people, planet, and profit, and it's what you value determines on how policy needs to be written. So we looked at alternative energies, carbon capture, and energy efficiency in our lab as possible solutions. And so then we're also looking at our carbon dioxide levels. And so one of our other driving questions was how fast is climate changing, and how does our carbon dioxide compare historically? And so when we start to think about this, we need to think about whether we're talking about long periods of time or short periods of time. So geologic timescales include all of Earth's history. So they tend to be hundreds and thousands of millions of years long. So very long periods of time. Human timescales, on the other hand, include only what would be considered approximately a human lifetime. So decades, centuries, or less. So a very short period of time. And then the reason why we need to understand timescales is because that tells us the rate or change and how fast climate change is happening. So this is an example of a graph that we've got. And so when we look at this, one of the main things we're going to look at is what's on our x and our y-axis. So we can see our x-axis is thousands of years, and our y-axis is our carbon dioxide concentration in parts per million. And so because we're talking thousands of years, we would assume that it was a geologic time scale. But if you look, this last little chunk has been dropped into here. And so now we're looking at just a few centuries at a time. And so that would be a human time scale. So this graph really has both. And so then if we actually look at our data itself, we see that it drops as low as 180 parts per million, and it goes as high as 280 parts per million here. And we can also see the difference in our lines. If we notice, this line goes up really steeply and then kind of comes down at a little less of a steep angle. This one goes up very steeply and then comes down at less of an angle. And so what that tells us is carbon dioxide tends to go up very quickly and come down very slowly. So when we look at this more recent time scale, we can see that that is really going up very fast. And that's a normal trend pattern for when carbon dioxide has spiked in the past. What's different now, though, is the level of that. And even if we stretch this part out, so notice how we've got a red line, a green line, and a black line as part of this. So if we take and stretch that out over time, this is always interesting to me because teeny, middle, long, and then long, middle, teeny. So did they stretch it out evenly? I'm always curious about that. So this red line starts to look flat. Even the green line now is curving upwards, and the black is even going up steeply as well. So we can see kind of this, when we look at it in detail, still shows a drastic increase towards the end. And that industrial revolution happened about right in there. So when humans started adding carbon dioxide, happened in this time frame. So we kind of had that normal increase until that point, and then since the Industrial Revolution, we can see kind of what humans have done here. Carbon dioxide increases steep or fast, and it decreases gradually or slow. So that also means that Earth is going to heat faster than it cools. And so on a geologic time scale, those carbon dioxide levels never really got above 280 parts per million, and it was only a difference of about 100 parts per million between both the high and the low. But the inset shows that straight line up at the end is still going up at still that faster rate. And so we can tell humans are having an impact. If we look at this graph, this one's a little bit different. So the first thing to notice is this black line that goes kind of down the center of this one. That's our present day temperature. So we're comparing kind of all of these ancient temperatures to current day to see how it would compare, right? Our red line here, this one is our temperature reconstruction from oxygen isotope data. They can get that from sea creatures' shells, and it has to do with how warm the air was and what oxygen atom was used in those shells. So we can reconstruct temperature based on oxygen isotopes and fossil data. The blue line, on the other hand, so this one that's a little less wavy, is sea level data, and we can get that from fossils of corals. And the other thing to notice are these stars that we use to mark these mass extinction events. So you can see kind of mass extinctions written right there. And so again, what we've seen before, we're seeing in here is temperature and sea level both change, right? Neither one of those lines is straight. But if we look at that red line and we look at where those mass extinctions are, we have a mass extinction when it was really cold. We have a mass extinction when it was really hot. We had a mass extinction when it was really hot. We had a mass extinction, not when it was the coldest, but just before it was the coldest, and again, once it started warming up again. And so every time we have one of these temperature extremes, we get this mass extinction event. Now, the difference between then and all of these times here is those mass extinctions took thousands of years. And now we're seeing it happen in a much more human time scale, and it's happening very, very quickly. I'm going to link this link here on the video so that you can take a look at this cartoon. The thing to notice about this cartoon is as you scroll through this image by XKCD, notice the trend line for the temperature data as it goes down. And you'll notice like the slope of the line, it just barely changes over time, and you're having to scroll like mad until you get to the end. There's some interesting little cartoons in there too, kind of makes it a little bit fun. But that goes to kind of also show you in another way what that difference between that geologic timescale is and then what's happening currently, and it gives you a good idea. At the end of this one, there are 3 projected lines, so one's kind of they kind of go like that. So this one would be worst case scenario. This one would be kind of mediocre scenario, and this would be best case scenario. We are almost always on the path that is the worst case scenario, unfortunately. So then when we start to think about human time scale impacts, one of the things when we first started talking about habitat loss was corals. So if we think about this in terms of our habitats, a coral bleaching event will take 10 to 12 years for that coral to recover, and only a 2-degree change causes coral bleaching. So as you look at this cartoon and you think about that 2-degree change, think about how long it's going to take for just our corals to recover. So that's another thing to think about. Again, I'm going to link this one. This is a YouTube video for this temperature visualization. On this one's a human time scale. And what you're going to see is that your x-axis goes around these barrels like this. And then you have carbon dioxide over here on the left, and you have temperature over here on the right-hand side. So it's comparing these two bits of data to each other over the course of a human lifetime. And so what we would see here on this one is that these two are related. When one goes up, the other goes up. And it's kind of one of those chicken and the egg situations. Which came first, the temperature to increase the capacity for carbon dioxide, or was it the carbon dioxide that started the temperature? Kind of doesn't matter, and because they're both going up anyway, and they're both going to have a positive feedback loop on each other. The thing we need to know is that temperature is increasing, and we might not notice it in any given season, but over the course of your lifetime, you will notice. And so my personal example of this is my kids, when they were little, would have to wear their Halloween costumes with coats over them, and then when they were bigger kids, they didn't. So I saw that in my lifetime. Again, I'm gonna link the video here on screen so you can go check this one out. This one's an ice visualization. So on this one, we are looking at the two separate polar ice caps and then kind of them together as a whole. And so time goes around our axis. Actually, it goes around this way. Sorry about that. And then the ice area goes in for lower and out for higher. And so what we see here is a human time scale. One of the cool pieces of this is you can actually see thermal inertia. So if you think of winter in the northern hemisphere, so we would be looking at this little circle here. Winter occurs, January, February, but we see our heaviest ice, our largest amount of ice in February, March, because of that thermal inertia. And our hottest months are probably July, August, but we don't see the least amount of ice until that August, September, October area because of that thermal inertia. Things that are hot stay hot, things that are cold stay cold. And so our ice caps are also showing that thermal inertia that we talked about. The other thing, as you watch this video, what you'll notice is all of these circles move inward. So you might have to watch it a couple times to see all of them. It's not a constant inward, so that's why these lines are wavy. There's some variance in that line, but overall our trend is that it's decreasing, which lowers our albedo. Again, that positive feedback loop. The last one is also for when we hear those things like, hey, climate change has happened in the past. This graph is a gnarly beast. So one of the things to notice right away is notice how on our x-axis we have time, but notice how it changes scale as it goes across. And so this symbol right here that happens on each of these rectangle points tells you that there's a change of scale or time. So each time you see one of these, you can kind of think of it as like zooming in on that data. So this data would have continued, and then as you zoomed in, it would have like an up line right here, and then you can see the finer points within that particular piece of data. So there's a change of units. And so when we look at that graph, we see that global temperatures have been way higher before. This is plus 14 degrees Celsius hotter than it currently is, right? So that's like way hotter than where we are now, right? Which you think, okay, so, and it's also been colder than it is, right? Than we've ever experienced. So what's the big deal? Well, back here, our globe had these wild temperature swings, right? But humans didn't exist yet. So if we zoom in on just this end bit, where we see is humans first appear about right here. So not until way down here on this end of the graph did humans first show up. And what we saw was a couple of ice ages and this nice stable climate in here. Look how flat that line is in comparison. Now we're zoomed way in, but we can still see that yes, there's some zigzagginess, but the overall trend is pretty stable. We do see one little baby ice age right in there. And so this one's pretty much geologic time, but what we want you to take from this, carbon dioxide is going way faster than it has in the past. And the climate was both hotter and colder and more unstable before humans were around. But on that human time scale, the climate was stable until recently. So humans are changing that climate. And even though it was hotter before, humans weren't alive then, and so we don't know how our human body's going to respond to those hotter temperatures. And then that temperature projection on the end. So if we look way down here over at this end, we see these two dots right here. So they had to put dots because the line kind of disappears off the end of the graph. But what we notice is where humans have appeared was right in here, right? And if we draw a straight line across, that's by 2100, we're expected to go above where humans have ever had to function in before. And so we're going to learn some stuff. about ourselves, about our priorities, about our values, because those temperatures go above where humans have ever been before. Okay, well, that's your time scale notes. Good luck on the exam.